Welcome. In this session, we will look at the relationship between continuity and differentiability. We can think of continuity in terms of approximations. To say that f is continuous at c means that limit of f of x as x approaches c is f of c. Intuitively, this just says that as we make x closer and closer to c, f of x gets closer and closer to f of c. In particular, for x close to c, f of x is close to f of c. What about differentiability? Differentiability says that f of x minus f of c over x minus c has limit f prime of c, yes, regular number. So f of x minus f of c over x minus c is approximately f prime of c, and the approximation gets better as we make x closer to c. So if I cross multiply, it says that f of x minus f of c is approximately f prime of c times x minus c, and the error in this approximation is x minus c times the error, the approximation of f of x minus f of c over x minus c. So the error in this approximation is small compared to x minus c. So note that in particular, this says that if x is close to c, then f of x minus f of c is proportional to x minus c, so that's close to 0, or f of x is close to f of c. So this says that if f is differentiable, it's continuous. It also indicates that to say something is differentiable is a stronger statement than saying that it is continuous. So we can expect that a function that's continuous may not be differentiable. We will look at two examples that confirm this. These are the kind of things that can happen with rather simple types of functions we've been looking at. The first type of non-differentiable continuous function is a function with a corner. The simplest familiar function of that type is absolute value function. We'll first use the definition to show that it's not differentiable at 0. So I find the difference quotient of absolute value of x at 0. This is absolute value of x minus absolute value of 0 over x minus 0. This is absolute value of x over x. To find the limit, because this is not an algebraic expression, I have to look at positive and negative values of x separately. If x is positive, absolute value of x is x. So absolute value of x over x is 1. But if x is negative, absolute value of x is the opposite of x. So I get minus x over x, which is negative 1. So the one-sided limits exist, but they are different. So there is no two-sided limit. We can extend the concept of derivative to talk about left-hand and right-hand derivatives. The definition is what you would expect. You do the difference quotient and then right-hand and left-hand limits. For a function to have a corner means that these limits exist under finite numbers but are different. We won't really have much use for these types of functions, except if the corner is not really a corner and the two limits end up being the same. Since we mostly deal with elementary functions, I won't say much more about these types of functions. Okay. The next type of continuous non-differentiable functions are functions with vertical tangents. The simplest such example is the cube root of x. Again, let's do the difference quotient. Cube root of x minus cube root of 0 over x minus 0 is x to the power 1/3 over x, which is 1 over x to the power 2/3. As x approaches 0, the denominator approaches 0. The numerator is constant at 1, so we know the limit is infinite, at least on each side. If x is non-zero, x power 2/3 is square of a non-zero number, so it's positive, whether x is positive or negative. So the limit is infinity from both sides, and this tells me the graph has a vertical tangent. Differentiability requires that the limit be a regular number, a finite number, so this is not differentiable at 0 either. In fact, typically any function with the exponent between 0 and 1 will be continuous but not differentiable, where the number inside the radical or the quantity inside the radical is 0. This will be relevant to us when we talk about critical points and critical values in chapter 30. Before we leave this topic, I want to show you in terms of graphs what this means. First, let's take a differentiable function. We'll take x cubed. So what does it mean to say that f of x minus f of c over x minus c is approximately a number for x close to c? It says rise over run doesn't change much. If the rise over run doesn't change at all, we know the function is a straight line, linear function. If it doesn't change very much, it should be approximately a straight line. Of course, if you take a big piece of the graph, like here, from 0 to 2, the curve is very visible. But if we zoom in, so let's zoom in by a factor of 10, the graph looks more or less straight. It's not quite straight, which you can verify if you put a ruler against the graph, you will see a slight bend. But if I zoom in by another factor of 10, even with a ruler, you won't be able to tell that this is not a straight line unless you know the equation. This is basically what happens with all differentiable functions. You select a point where it's differentiable, keep zooming in, the graph eventually will look like a straight line, and the slope of this straight line, or approximate straight line to be precise, is the derivative. What about the two non-differentiable functions we looked at? The first was absolute value of x, which I said has a corner. And that's what you see in the graph. What if I zoom in on this graph at the origin? So if zoomed in by a factor of 10, it still looks like a V. Still there is a corner. I zoomed in by another factor of 10, so factor of 100 altogether. No difference. In fact, no matter how much you zoom in, you still get a corner. That's what we saw in our algebraic calculation. The slopes on the right and left are different. The next example was the cube root of x. I have a somewhat strange window here. That's because of what's going to come next. You can see that there is a slight curve in the middle. It doesn't increase very fast, so that's why it looks almost flat, but the curve in the bend in the middle is still visible. If I zoom in by a factor of 10, then the curve is more visible. But note that the curve doesn't look as flat as before. If I zoom in by another factor of 10, so 100 altogether, the graph looks almost vertical. Because of limitations of the graphing program, I cannot zoom in any further and have a nice looking graph. This is basically what it means to have infinite derivative, so to speak. As you zoom in, the graph looks more and more vertical. It's also possible to have a combination of these two, what's called a cusp, which you will see in the graph of x to the power 2/3. A large piece of the graph looks like a bent V, or like the pictures of birds you draw in cartoons or little children's drawings. Just two big wings coming out of the origin. If I zoom in, as I zoom in, the two wings become more and more vertical. Here I've zoomed in by a factor of 10. The angle of the V is sharper. The wings rise faster, more steeply. Another factor of 10, the wings are almost straight up. The next one, both of them will just end up being almost vertical to the naked eye. So this is another possibility when you have an exponent between 0 and 1. So this concludes our look at the connection between continuity and differentiability, and I will stop this session here.